well, in the next couple classes, we'll do renewable resources. And what's sort of at the basis in thinking about resources is that we're in multiple time periods. What we want to do in resources is plan a pathway of how much we should harvest now and how much we should harvest in the next period. So I'll give you two really simple models, one for non-renewable, one for renewable, two for renewable, that will be models about how much to harvest in each time period. And we'll still be using the stuff we learned in the last two classes about interest rates because that's the way that we relate money between different time periods. We have this idea we can use money now, can use money in the future, we're impatient to use it now. We have the present value, that's a way to convert money in the future into money now. That's going to capture our impatience. I'm going to do some examples. The main one in the book, if you're following along hopefully in the book that I'll walk through, is the issue of old growth redwood. Usually we think of trees and forestry as renewable resources. The tree will grow again. How often should we grow the tree and regrow it? But this chapter motivates it as non-renewable resources because old growth redwoods took thousands of years to make old growth, and we're going to consume it within this small period of modern industrial civilization that just sort of consumes what it can, much smaller than the time period that would take to regrow thousands of year old trees. So we're mining old growth redwood like it's just a fixed stock. That's how much there is. And we'll go through the hoteling model, which is the basic model for resources for non-renewable resources. So just to think through the types of resources, to think what sort of boxes we're going to fit our different models in, there's two basic things. There's non-renewable resources and renewable resources. And in our non-renewable resources, usually we're thinking about mineral resources, right? Oil, coal, gas, ore, diamonds, gold, silver. What are like the really strange elements in our cell phone? There's like weird coltan or something like that. There's only like so much of it in the world, and there's only such a rate that we can get it out. There's some non-mineral, like non-rocks and oil, resources, and this textbook will motivate this one of the old growth redwood, where it's just something where there's a stock of it when we came into our industrial capacity to harvest things, and we're going to use it up over some time path. Most of the rest of resources and resource economics is about renewable resources. We already think about it. We've already started talking some about agriculture. Soil is a renewable resource. We can use it up. It can run away, and then we can renew it. We can rebuild our soil. So soil fertility itself as a stock is something we can use some of to grow, and we can renew it. Water is definitely a renewable resource. We've already started to talk about. We'll talk about more later. How much we pull out of the groundwater. If we relax that, that can be renewed, or even year to year, how much water to take out of our complicated irrigation system. Our other renewable resources we've already talked about is for power, for electricity. We have wind, we have solar, we have hydro as part of how we're making power. But the ones that we'll talk about in class in the next two lectures are forestry and fisheries. Forestry, what is the optimal rotation cycle? Some of you might be forestry majors. We're in the forestry building here, so there's like a whole science and there's a whole field of study about how to grow optimal forests. In economics, some of the basic questions is just like when to harvest, how long to let things regrow until you harvest them again. Fisheries, it's about the growth function. The fishery is out in the forest, out in the ocean growing, regrowing the amount of fish. Fish are spawning, and we're harvesting a certain amount of fish. They're regrowing, and what's the right amount of fish to allow to be caught, and where are we on sort of the population curve of fish growth? So we're today going to be mostly in non-renewable resources. And within non-renewable resources, we can think about a typology of how available and how economically available these are for us. So we say, I'll show you a graph for this, but our beginning term is current reserves. So current reserves, we can take an example, coal, oil, natural gas, gold. How much is there on the planet? How much do we know it's been mapped where it is? And how much of that can be, how much of the resources that we have mapped can be extracted at our current economic levels? At the current prices we're at, will be extractable. There's always going to be some reserves that are going to be so remote or so far away or so difficult or so environmentally costly that they won't be extracted. Then we have potential reserves. These are reserves that are known and they're mapped, but they won't be extracted at current prices. They could be extracted at much higher prices. In the case of copper, we have a lot of copper in the United States. We used to have a lot of copper mines. They've mostly moved overseas. Most of the copper now comes from Chile. We have just as much copper in Colorado as we did when copper mining moved to Chile, but it became a lot cheaper for the Chileans to mine than for us to mine. Those reserves are still there. Sometime in the future, when the price of copper goes up even more, those mines in Chile, in Colorado and Montana will reopen and be extracting again. We also think about the resource endowment, so the total amount of resources that there are. We can think about the endowment just for a mine owner or just for a region, or we can think about it globally. So here's a classification that's from the U.S. Geological Survey here. The government has a branch that deals with minerals and geology. So what we are basically looking at most of the time is economically available resources that have been identified. They've been measured. We know where they are. There's a whole area of reserves that we haven't gotten to yet that probably is there once we drill and once we explore. So a lot of times this is a big area. They're economic, but we haven't quite mapped them. We don't quite know where they are. And then these areas where it's not, at the current prices, it's not going to work. They're not economically viable now, but if the prices were higher, we would know where they were, right? From there, there's a whole bunch of other resources that they might be out there. We know from the conditions in the geology and plate tectonics where there might be more resources and where it might be able to mine them in the future. So one thing I want to try and get to at the end, a big thing that's happening right now is fracking, right? So a new technology came along where a whole bunch of natural gas that was always there became available to us. They figured out how to fracture rock and get tons of natural gas out of it that they weren't able to. And this is really recent. This is like the last 5 or 10 years. And it's related to economic because they changed the technology for getting gas out of the ground, and they're getting it out of the ground at super low prices. The price of natural gas is super low right now. And the United States has a ton of it. I've already tried to talk about that a little bit. So we're moving into this area here, right, where we had reserves that we knew what they were, and then we had a change in technology, and we moved and we opened up a new box of natural gas. We have also talked about previously about coal. We had a whole bunch of areas with coal where it's tapped out, and the coal in the United States is now coming from a different area of the United States than it was previously. We changed the prices of coal by requiring them to burn low sulfur coal. They were previously burning coal from Appalachia, and we said, you need to burn this low sulfur coal because it'll cause less sulfur dioxide. So we changed conditions on what was economic and not economic, and we opened up a new area for coal mining. That's the main area for coal mining now in the United States. And so we've moved coal mining from the cheaper one under Appalachia to this more expensive one in Wyoming, Montana that's sort of expanded and exploded. So we can think about a lot of these questions we have about non-renewable resources, different sources of carbon as different boxes on this, and our economic conditions are changing where we are on there. So fracking. So we sit on top of, our state has a huge area called the Monterey Shale. There is proposed, this is that thing where nobody really knows exactly how much oil is in there, right? So the Monterey Shale has elements of these 3 boxes here, or maybe these 4 boxes, okay? So you can go to Los Angeles, you can drive through Los Angeles, and you'll see the oil wells pumping in the middle of Los Angeles. You'll see the La Brea tar pits. You go through Kona Lake Coalinga, if you go on the 101, you can see the oil wells pumping. They've been pumping most of this century, right? But if we have this new technique where we can send pipelines horizontally and break open seams and go much deeper, this is crazy deep, right? Those old wells that have been pumping for 100 years, they're not 15,000 feet deep. These are new technologies that are going to get us 15,000 feet deep. So the big question right now is they propose, we have new technologies, we have new ways to map down there, but will they be economically recoverable? There might be oil 15,000 feet down trapped in some seam, but will it be, under $100 a barrel to get it out? Or if it's into the future, under $150 a barrel to get it out. It's a weird time. The governor is super excited about fracking. We have Jerry Brown, super lefty environmental governor. But the potential for revenue for the state of California and the potential for so here's a quote from the Wall Street Journal. The overall economic benefits to open up the Monterey Shale field could reach $1 trillion, right? Let's take 15 billion barrels and multiply it times 100, 150, 200, whatever we want to multiply it by. One can only imagine the impact on California's education system, social programs, infrastructure, even energy tech R&D. Moreover, with that kind of revenue, Sacramento tax collections could wipe out debt and deficits. So Jerry Brown's big thing is balancing the state budget, and this promise of we're going to start leasing fields that nobody has thought is interesting before, going to generate a lot of money. And if you read what you want into the sentence, you can say, oh, well, maybe the tuition won't go up so much if we have these fracking fields opening up. Nobody really knows what's going to happen. I would say this is speculative right now. Some of the, the doomsayers on the green side would be like, it's coming, we have to stop it now. I think that, they're fighting about this in the legislature, and there's some question of how much will this ever get going. Here's a map of where it is. So if we think about, we already know that, we go to Santa Barbara and there's already, we already can see those oil platforms out there. As I said, we can go in Los Angeles and we can see those oil wells in the middle of Los Angeles. We go down I-5, we can see some oil fields. So there's so the light yellow here are the areas that are currently being exploited. Bakersfield. But the area that could be opened up with fracking is much, much bigger, right? So this takes, this area around Bakersfield and makes it go the whole San Joaquin Valley. This opens up the whole Salinas Valley, not just that area by Atascadero. It opens a whole bunch of new areas. And we have different environmental conditions in each of these areas and different, different reasons that fracking could be really dangerous. We have the most valuable agriculture in the world that's already driving our economy here, right? We have, billions of dollars of almond orchards here. We got to take care of those. We have a huge city, one of the biggest cities in the world here on top of this one. We have the Santa Barbara area. They have no water. They have no water coming from outside the other side of the state. They have only the water that lands in Santa Barbara. So how are they going to start to run, these much bigger operations that require tons of water? So fracking, some of the big questions are, can it be done safely? This technology is brand new and it's evolving. It's just, they're just figuring out how to do it right and to do it at least cost. One thing that you need to know about it is they use tons of water. They inject water down into the earth and use that to crack open the earth, and that's how they get the oil and the gas to bubble out that was locked in there anyways. So it uses tons of water. Big red flag in California. We don't have tons of water. All of our water is allocated, and we're fighting over it already. We're having a drought. With climate change, maybe we'll have droughts more frequently. So you say, we had a lot of fracking, and it was this year, and we're down to 30, 40% of our water. And say price of oil was up to $150 a gallon. There would be oil wells taking fresh water from snowmelt in the Sierras that wasn't going to farms, that wasn't going to people. And are we ready as a society to make that trade-off? We'd rather have oil than a fresh water supply. One other thing that they do is when they inject the water down there, they put these special chemicals in that sort of lubricate it and make it, some attributes of how they want to fracture the shale. These chemicals are treated as industrial trade secrets, and they're not allowed to require the companies to release what the chemicals are. So usually the way we regulate things is we know what they are, we can do measurements, we can do epidemiology, we can do this public health hazard that I tried to motivate, and then we figure out how to get into the environment. But right now this thing is so new and this, it's all patented and highly closely held by these new companies that we don't have good enough regulations on these new chemicals that are newly being used. And we have a long history in the environmental regulation side where there's something new, we don't regulate it, later we find out unintended consequences, and we, DDT, something like that, where seemed like a great new chemical. Then later we had to go back and mediate all these things that it brought. A whole bunch of water comes out. So you have a whole bunch of water that can be polluted from oil and gas, and can be polluted from these chemicals, and it can come back out of the fracking operation and pool up until you get huge lagoons and ponds of polluted water to deal with. This is one of the big ones that, if you've heard stuff about fracking, this can be a big problem. This water can get out into the groundwater, or it can be out into ponds, and companies don't do a good job with it, and this pond will break and flood somebody's fields. So it's creating a whole bunch of toxic water. That's not as much of a problem for regular oil fields, but is part of this fracking thing. The other thing that we have in California, this is sort of unclear, probably not a problem, but is of concern, is can you cause earthquakes? You're going under the earth, you're breaking up the shale, and we have just been having so many earthquakes lately, and the places where this is, definitely on top of fault lines. Where it happens in Los Angeles, there's definitely fault lines there. So if there's a chance that fracking causes earthquakes, we are living in a place where a lot of people would be affected by this kind of seismicity. One thing that might be an issue with fracking is better done in places where there haven't been earthquakes, where these sort of striations, there's shale and it's sort of locked up like this. Fracking, you drill in and then you sort of break these so you can get the oil and the gas to bubble up. There's some idea that in California there's been lots of earthquakes over time, constantly small earthquakes, and these things are already broken, and so maybe fracking won't yield as much of a benefit as it has in North Dakota or Oklahoma or the places where it's going big right now. All right, going back to resource economics, we need to think about it as a dynamic question. Should be able to remember resource economics, dynamic model. They're linked in your brain, multiple time periods. Resources means multiple time periods. A resource model means there'll be interest rates in it. We'll be able to just think that those are going to go together. So we have two words for that. We have static, which means one time period, and dynamic, which means multiple time period. Dynamic in economics means a multiple time period model, a model with time in it. So most of what we did up to the midterm certainly was a one time period model. Supply, demand, quantity, we didn't have time in there. We've done interest, we've done benefit cost, we've started to think about dynamics and present values. So resource owners are having questions about this period versus the future. Time is an important part of the model. Dynamic models. So I'm going to start doing a little bit of math and a little bit of graphing. So hopefully you guys can follow along and help me. So we'll start out with the simple model that we learned from before the midterm. Okay? So we have a demand curve, price equals 8 minus 0.4 times Q. We have a constant marginal cost to extract this resource of 2. So we need to set price equals to marginal cost to solve for the level of Q. So this is, some review from early on. We have marginal cost equals to the price. That's what this firm's going to do their output. So it's 8 minus 0.4 Q. So anybody see what Q is going to be? It's really fast. Solve for Q, quick. Let's put 0.4 Q over here. And we'll subtract the 2. We got 6. Q equals 6 over 0.4. What's that? 15. Okay. So Q is going to be equal to 15. And then we had we're always, these simple cases, we can certainly graph them. Here's our price. Here's our quantity. A demand curve, first day of class. So this intercept is 8, right? That's where we're starting, 8. And then the slope is minus 0.4. And then we have the marginal cost here at 2. And then we found that marginal cost hits the demand curve at 15. Does that make sense to people? It's easy following along? Okay, we'll make it more complicated. We don't want you to think things are easy. Okay, so we have 2 time periods now, right? We're going to start with a 2 time period model. So we have in period 1, we just did that one. And then we'll have the same thing in period 2. So we have period 2. Now the same marginal cost curve, the same solution at 15. So in Q2, that would also equal to 15. So if we had 2 time periods, we would consume Q1 plus Q2 equals 30. So if we were just setting price equal to marginal cost, we would consume 30 units from the 2 time periods. But let's make this a little more complicated now. Let's make it a dynamic model, and let's say we have only so much quantity to consume. There's only so much oil, there's only so much in our mine, and we have to figure out how to spread it over 2 years. So in our first case, we had Q1 plus Q2 equals 15, and each time period equals 30. Let's now restrict that to 20. Let's say there's only going to be 20 units total available. And let's switch to net benefits. So this would be marginal benefit minus marginal cost. Let's switch that out. I can do the math for that. And then the important part, the second period, we want to put that in present value terms, like we did in the last 2 lectures, by discounting it into first period, so that we're making all of our decisions in first period dollars, first period money. Okay, so let's make net benefits, just because simpler. Marginal revenue minus marginal cost, 8 minus 0.4 Q was our price and marginal revenue. Marginal cost was 2. So now our net benefits, 8 minus 2 is 6, minus 0.4 Q would be our net benefit equation. Now we need to the other math we need to do is we need to discount the second time period into the first time period. So we'll just do a simple interest rate of 10% and just one time period, but I want you guys to think about, if I asked you to do it with a different interest rate or a different time period, how this multiplier would change. So it's going to be the net benefits times 1 over 1 plus 0.1 to the 1, because that's one time period and the interest rate is 10%. So it's going to equal the net benefits. This is the net benefit in time period 1 equals the net benefit in time period 2 times this discounting factor. So the net benefit 1 over 1.1, right? So let's think about this term. That's also, what's 1 over 1.1? 0.909. So this little term is our discounting term. This 0.9 is our discounting term, the amount that the next time period's benefits we're going to depreciate into this time period. So let's combine these two, right? So the net benefit in period 1 is going to equal this net benefit 6 minus 0.4 Q times this depreciation term, right? Net benefit in 1. So 9.09 times 6 is 5.45 minus 9 times 4, 0.36 Q. Right? So we have this adjusted demand curve that's going to be for our depreciating our second period benefits into our first period values. So we want to graph this. The way that we graph things with a fixed quantity, as we've done in tradable permits, is with a graph with a fixed width. Right? So there's only 20 units available in this graph. We did this in marginal cost for abatement when we had 2 different sectors polluting and they only had so much pollution they could fill up. Here we're going to say there's only 20 units available between period 1 and period 2. So on the bottom of the graph, period 1 is going to be going this way up to the 20 units, and period 2 is going to be going this way from this axis. Does that make sense? So we have to fit both of our consumptions into this graph, both of our levels of extraction into this graph. So we started